Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Shaheer bin Zaid. I'm from 2BEE 1/1. Today I will discussing about the let file control principle that is titled a system response. So basically, which is we have divided two parts. Like first, this part A is system response for first order. And secondly, we have been given the part B, that is system response for second order. So part A, we have given the closed loop transfer function. This is the block diagram for the block diagram for closed loop transfer function, and we have given the value that k is equal to 12 and a is equal to 4. So first we have to find the transfer function according to the calculation that I have done. The transfer function I get is 12 is 12 over s plus 16. So from the transfer function I have obtained, I have put the transfer function inside the MATLAB coding, and as is shown in here, we have numerator is 12 and denominator is 1 and 16. And then to produce the graph, we have command grid, and the graph will appear like this. So firstly, we want to find the final value. We have to right click at the graph in the blue line, and we get the final value is 0.75. After we obtain the final value, we can calculate the other time by using the final value. First, after we have get the final value, after that we can obtain the other time, that is we need to find the time constant t, rest time tr, and the settling time ts of the system. So for the time constant, I get the 0.0622. For the time rush, I get a 0.1374, and for the settling time, I get the 0.245. And at the graph, we just label. It is I have labeled 0.0622. There is a time constant, and then at the 0.137, we have a time rise. The amplitude is 0.666, and the time settling time is 0.245, and the amplitude is 0.735. So we move to part B. that is a second order. For the part B, we have been given the RLC circuit, and then we have given the natural frequency and damping ratio. We have a different damping ratio and different condition, and then which is condition 1 is 0, condition 2 is 0.2, condition 3 is 1, condition 4 is 2. So from the circuit, we can produce the transfer function. And lastly, we have obtained the natural frequency is 1, and then we can find the resistance every condition that we have that have a different damping ratio. Okay, for the condition 1, we have get 0, condition 3. Okay, from the value that we have get from the calculation, I will put inside the simulating model to produce graph. So for the condition 1, we have option that we produce the graph, and this is undamped response. For condition 2, we have 0.4 resistance. So the graph we get the undamped response. Condition 3 is 2 millisecond at 2 milliohm. So we have the graph that shows the critically damped response, and for the condition 4, we have 4 milliohm. So we insert in the simulated model, and we show that we show the overdamped response. So for the damp ratio, for the damp response, every damp response is different according to their respective ratio. For the underdamped is the damping ratio is always less than 1. This is for the underdamped. And then we have critically damped, which is always equal to 1. So we have 1 is the damping ratio, and for condition 4, we have 1 for the damping ratio. For the condition 4, that is over the response. Um, for the overturn response for the condition 4, more than 1, so it's equal to overturn response. So that's all for me for the lab 5 system response. Okay, thank you.